This is a class video for Tuesday, September 29th. So the opener on Tuesday was to write the electron configuration for silicon. Before we start on the electron configuration, we need to know how many electrons there are in silicon. So the atomic number for silicon is 14. Therefore, the number of electrons is 14 electrons. We've got to put those into subshells according to the Aufbau principle. So the first subshell to be filled is the 1s. So let's put 2 electrons in there. S subshells always take 2 electrons. Then we have 2s2. After that, 2p6. P subshells can fill up to 6 electrons, can hold up to 6 electrons. That takes care of 10 electrons so far. So after that, we go to 3s2 and then 3p2. Okay, so then the second question is, what is the valence shell electron configuration? So the valence shell is the outermost, shell in the atom. Okay, the highest energy level shell. So what we need to do is find the subshells that have the highest energy level. The energy level is given by the number in front here. So we can see that the highest energy level is the third energy level. Okay, so both the 3s2 and the 3p2 are in the third energy level. And so the valence shell electron configuration is 3s2, 3p2. That's our valence shell electron configuration. All right, so topic 1.5 is on atomic structure and electron configuration. And one of the things that's going to come into play here is an awesome rule of nature. This is Coulomb's law of electrostatics. And we will talk a lot more about Coulomb's law in a bit. So to start us off, we're going to be looking at the Bohr model. So the Bohr model is a great model for thinking about the electrons in an atom and how they're arranged. It's not a complete picture of the atom, but it's a very good model for thinking about how electrons and the nucleus interact. So we got a few definitions that we want to define here. So first of all, the nuclear charge, is the charge, exactly what it sounds like. It's the positive charge of the nucleus. Okay, and positive charge in an atom comes from the proton. So this positive charge of the nucleus is equal to the number of protons. Now, the effective nuclear charge is the charge that particular atoms, particular electrons, specific electrons experience from the nucleus. Okay, so looking at something like a lithium atom right here, we can see that we have 1 valence electron in the outermost shell of lithium. That's our 2s1 electron. And we have 2 electrons in the 1s subshell. So if I can circle this, maybe I'll use a different color. So these 2, these are the core electrons. Oh, that got thick all of a sudden. Okay, so those are our core electrons right there. And then this 1 valence electron is, that is our valence electron. Okay, we got to make this a lot thinner. Okay, so we've got 1 valence electron, 2 core electrons in lithium. Okay, what do you think? are the core electrons and the valence electrons going to experience the same charge, same nuclear charge from the lithium nucleus? Well, these core electrons are right next to the nucleus. They're going to feel the full positive 3 charge of the nucleus. However, this valence electron of lithium, okay, let me redraw this because it's hard to see. So in lithium, we got a +3, okay, and then we've got 2 core electrons, so 1, 2, okay, and those are our 1s2 core electrons, okay, and then we have an outer valence electron, 2s1, okay, that's our valence electron. So we have 2 core electrons and we have 1 valence electron. Well, the core is going to feel this full positive 3 charge from the nucleus. These electrons are right next to, okay, directly next to the nucleus, directly, the nucleus is not at all like, disconnected from them. However, if we look at this valence electron cannot feel the full force of the nucleus because there are these 2 core electrons that are shielding or screening the positive charge of the nucleus. So that is the shielding or screening effect. This is when core electrons, okay, shield or block some of the nuclear charge okay, the nuclear charge causing the valence electrons to feel less attraction for the nucleus. Those valence electrons will be less tightly held, okay, because they can't feel that attractive force as much. Remember, positive and negative will attract. Electrons are negative, the nucleus is positive. So when these core electrons shield or block some of that nuclear charge for the valence electrons, that's called the shielding or the screening effect. Okay, so that will explain some of the kind of the reactivity of these valence electrons, the ease with which they're removed sometimes, or the ease with which they're added. And so that's these concepts are going to come up in periodic trends. Okay, but going back to the Bohr model for a second, the Bohr model is a great model, okay, but actually electrons do not orbit the nucleus like this. They don't go in planetary orbits around the nucleus as Bohr imagined. The real picture, the real model that we have right now is the quantum model. And the quantum model is based on Schrodinger's equation. And in the quantum model, electrons are in orbitals. Orbitals are these regions of space, okay, just kind of defined areas in which there's a very high probability of finding the electron. So like something above 90%. This is where you can find, 90 to 98% of the electron density. Okay, you can be assured of finding that percentage of the electron, not that percentage, but the probability of that electron being there is very high. So the electrons take on things that are more like electron clouds. And these orbitals are the electron clouds. And these orbitals have shapes. Okay, so the s orbital is a round sphere. P orbitals are these kind of dumbbell shapes, and there's 3 of them. And d orbitals are these more like clover leaf, and this d DZ orbital is even crazier. But the upshot is you don't need to know the shapes of these orbitals unless you really enjoy shapes. But each orbital can hold 2 electrons, okay, with opposite spin. Okay, and we're going to go into electron configuration in a moment. Now note that these orbitals are based on the hydrogen orbitals. After hydrogen, we cannot solve exactly for the energies of the orbitals. So we use the hydrogen orbitals as models. Hydrogen is 1 electron and 1 proton. We can solve for that. When you add another electron in, it's no longer possible to solve the energies, to get the energies for the orbitals. Okay, so for many electron atoms, we use the hydrogen orbitals as the basis. Okay, and so if you want to take a look at this link, it's kind of a neat link. You can see the shapes of orbitals if you're interested in that. Here are the F orbitals. Okay, they look even crazier, like little flowers or something. Okay, so here's our Aufbau rule, our Aufbau principle that we use to write the electron configuration of silicon. So the Aufbau principle tells us which orbitals and the order in which we fill the orbitals or the subshells. Okay, so these different, the S, the P, the D, and the F, these are different subshells. So this is a subshell. This whole row, anything with the same energy level, this is a shell. So the 1s is a shell. This 2s, 2p is a shell. Here's the 3rd shell. Here's the 4th, okay, and so forth. So those are the shells. These are the subshells, and within the subshells, there are orbitals. Okay, so the S subshell holds only 2 electrons because it only has 1 orbital. The P subshell, okay, has 3 orbitals, so it can hold up to 6 electrons. The D has 5 orbitals, so it can hold up to 10. The F subshells have 7 orbitals, so they can hold up to 14 electrons. So a couple examples here. So let's just start off with a relatively easy example. So phosphorus, number 15 on the periodic table. Again, here we're going to start with 1s2. Okay, so there's our first. We follow these arrows. The next subshell we fill is 2s2. The next one we fill is 2p6. So I'm up to 10 there. The next one we fill is 3s2. Okay, then after that, p3. Okay, so that's our electron configuration for phosphorus. All right, what about a transition metal like, let's take something like chromium. Okay, so chromium, if we look on the periodic table, is number, should take a look, it's next to manganese, it's number 24. So it has 24 electrons. All right, so again here, let's start with 1s2, 2s2, 2p6, okay, 3s2, 3p6. Okay, we're up to 18 now. Now look at this. After the 3p, we go to 4s. 4s lies lower in energy, okay, than 3d, and then after that, we can put in 3d4 for a total of 24 electrons. All right, so that's our electron configuration for chromium. What's our valence shell electrons here? Well, here's our valence shell for phosphorus. and we have 5 valence electrons. Okay, for chromium, here's our valence shell. There's 2 electrons in 4s. So often people will say you should rewrite this and put the 4s higher in energy. That's not absolutely necessary, but after the subshells are filled, it is true that the 4s is higher in energy. So if it helps you to remember, you may want to rewrite the configuration so that the subshells are in order of energy, so that the 4s is highest. It's up to you. It's just a little matter of making sure that you recognize that the 4s 2 electrons are the valence electrons in chromium. Okay, those are 2 examples. Now, the Aufbau principle is nice, but actually you don't even need to memorize the Aufbau principle because the periodic table is set up. The electron configuration is embedded into the periodic table. It's a feature of the periodic table. It's you know, that's the way it was naturally set up, I suppose. Maybe we shouldn't get into that, but okay. So if we look here, though, these first 2 groups, group 1 and group 2, okay, and helium over here, these are filling something called the S block. These are the S subshells. Their valence electrons will end in the S block. Okay, over here, group 13 through 18, except not helium, their electron configurations will end in the P block, in the P subshells. Here, the transition metals, these are called the transition elements, or the transition metals. Their configurations will end in a D subshell. Here we have the lanthanides and the actinides, the rare earths. Okay, their electron configurations will end in the F subshells. All right, so if we take a look here, the other thing, maybe we want to just review group 1. These are called the alkali metals: lithium, sodium, potassium. These are called the alkaline earths, alkaline earth metals. Okay, beryllium, magnesium, calcium, and so forth. Okay, then our group 18 is a very special group called the noble gases. Very royal. And then another special name for group 17, okay, are the halogens. Fluorine, chlorine, okay, bromine, iodine, astatine. Okay, so these are our special names for, and then we have other groups here like the oxygen group, the nitrogen group, carbon group, okay, the boron group. Those don't have special names. Sometimes we call the oxygen group the chalcogens, but you know, that's kind of an older term. Okay, so going on. Okay, so anyway, the upshot is the electron configurations. You don't have to know the Aufbau principle. You can read off the configuration from the periodic table. So for example, if I pick something like silicon here, which we did as the opener, I could just go across. I know it's 1s2, 2s2, 2p6, 3s2, 3p2 is what it ends in. Okay. Pretty nifty. All right, so here, our electron configuration for sulfur. We're going to write the entire thing. Sulfur has 16 electrons. 1s2, 2s2, right? We got 1s2, 2s2, now 2p6, 3s2, and then 3p, 1, 2, 3, 4, 3p4. There's my electron configuration. Now we're going to write something called the orbital notation, which shows how the electrons are in the actual orbitals. So what we do is we draw a line for each orbital in the subshell, and we put a little, label on it. And in each orbital, we can have up to 2 electrons, one spin up, one spin down. Okay, the next subshell is the 2s, so I draw 1 orbital because it's an s subshell, up and down. Okay, 2p, there are 3 orbitals for 2p. Now, when filling multiple orbitals in a single subshell, you always want to fill up, 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 put 1 electron into each empty orbital first, and then we go back and fill in the second electron. This is called, Hund's rule. The fact that we fill the empty orbitals first, or I like to call it the bus seat rule. When you get on the bus, you take the empty seats, and then if there is no empty seat, you go and sit down next to somebody. At least that's my experience in most buses. All right, so then after 2p, it's a s subshell 3s, so just 1 orbital here, fill that. And then p again has 3 orbitals, so 3p. And again, here we need to use Hund's rule. So up, up, up first, 1, 2, 3, and then we go back and we pair up that first orbital and put 2 electrons in there. Okay, now we're going to do some condensed electron configuration. Sometimes we call this the noble gas electron configuration. Now, so noble gases have this closed outer shell configuration. So they're very stable. And so we can kind of use that as a basis for our electron configuration and write a shorthand electron configuration. So if we look at iron and we go backwards in the periodic table, we come to our first noble gas that we hit is argon. So what we can do is we can write argon in brackets and then go forward from there. So after argon, we're going to go to 4s2, and then 1, 2, 3, 4, 5, 6, 3d6. So there's our condensed electron configuration for the iron atom. Now for iron 2+ ion, the 2+ means we've lost 2 electrons. So now we only have 24 electrons instead of 26. Okay, so now we take argon. Okay, but where are our valence electrons here? Well, look here. Here's our valence electrons. We have to lose our valence electrons first because those are the easiest to remove because they're in the outermost shell. So if we remove those 2 valence electrons, all we're left with is 3d6. Okay, so then Fe3+ means that we've lost 3 electrons. We now only have 23 electrons. So now we have argon. We lose the 4s and then 1 from the 3d. And we have 3d5. And if we look at the the orbital notation for 3d5, that's 5 unpaired electrons. Okay, and these unpaired electrons lead to something called paramagnetism, where the electron spins can align in a magnetic field. And in particular for iron is ferromagnetic. So if you align all these spins in iron, you can make it into a magnet. So that's very useful in our society for different things like electromagnets and just magnets are fun in general. Okay, but a natural piece of iron does not have spin aligned to begin with, right? It's kind of all over the place. Could be up, down. Okay, it's randomly oriented spins. So a normal piece of iron is not magnetic. You have to align the spins. There are magnetite, which is a iron ore, is one that has a high degree of orientation of its spin. So it is very slightly magnetic and can pick up things. Okay. Going on to the next, we're going to write the electron configurations for neon, F minus, and Mg plus 2. So neon, okay, has 10 electrons. So it's going to be 1s2, 2s2, 2p6. F minus, okay, now we got F, which is 9, but it gained 1 electron, so it also has 10 electrons, which means that it must have the same electron configuration as neon. That's why it wants to gain an electron. It can be like neon. Okay, so Mg plus 2. Mg normally has 12 electrons, but plus 2 means it lost 2, so it also has 10 electrons. It lost its 2 valence electrons and now looks like neon, a noble gas. So its electron configuration is also 1s2, 2s2, 2p6. When we have these, okay, these are same number of electrons. We have something called isoelectronic particles or series. Okay, so these 3 particles, these 3 species are called isoelectronic to each other. All right, so there's this worksheet. We just did that together. Okay, now the basic rule of nature that governs why things stick together, why stuff just attracts each other, is Coulomb's law. Coulomb's law is this equation here, but you do not need to know Coulomb's law, okay? You do not need to be able to calculate anything in Coulomb's law. And as someone noticed in class, okay, it looks a lot like the gravitational equation, okay, for gravity. And it's exactly the same form. Okay, so Coulomb's law says, basically, this is Coulomb's law of electrostatics. Oh, running out of space here. It says that the attractive or repulsive force between 2 charged particles. Okay, so basically I'm writing out kind of what Coulomb's law is implying here with this equation. Is directly related to the magnitude of the charges and to the inverse of the distance squared. Okay, so that's kind of the fancy schmancy definition for Coulomb's law. Now, what are the 2 implications, the 2 important implications? I'll write them down here. 2 important implications of Coulomb's law. This is kind of the gist of the whole law. So first, higher charges more force. Okay, now remember that positive and negative attract. Positive, same charges repel. So negative and negative repel. But Coulomb's law says that higher the charges, we have more force, more attractive force in the case of positive and negative, more repulsive force if we have higher charges with similar charges, but more force. Now for bonding, right, we're mostly looking at attractive force. Okay, second implication is the closer things, I shouldn't use the word things, closer the particles are, more attractive force. And again, here we're talking about bonding, and bonding requires some positive and negative attraction. So closer the particles are, we get more attractive force. Higher the charges are, we get more attractive force. So those are the two important implications of Coulomb's law. So going back to the isoelectronic series, we're going to apply Coulomb's law to these species. And the question is, if we had to remove an electron from these species, which of them would require the most energy to remove that electron and why? So going back here, remember, neon had 10 electrons. F minus had 10 electrons. Mg also had 10 electrons. Okay, they had exactly the same electron configurations. They all had 1s2, 2s2, 2p6, right? They had, that was their electron configuration. Now, the difference is, though, the nucleus, let's write down the nuclear charge for neon. For neon, the nuclear charge is plus 10, okay, atomic number 10. For fluorine, the charge is plus 9. For Mg, for magnesium, it's plus 12. Okay, so Coulomb's law says higher charges attract more attractive force. So here, 12 electrons can attract 10 electrons much better than 9 protons in the nucleus. Let me say that again because I may have said electrons twice. 12 protons in the nucleus, higher positive charge, can attract 10 electrons better than just 9 protons in the nucleus. Okay, so those 12 electrons can pull in those 10 electrons more tightly, which means that this will be hardest to remove an electron. Okay, and this is basically the easiest one to remove. Sorry, that's confusing. It will be hardest to remove an electron from Mg plus 2 because its nucleus has the highest charge here. It will be easiest to remove from F minus. Okay, so here, right again, here is the least positive charge, so the least attractive force between the nucleus and the electrons. All right, so going back to the Bohr model, again, we're going to apply Coulomb's law to this. Okay, we're going to imagine that we are an electron. okay, in the sodium atom. Okay, here's group 1. Each of them has 1 valence electron, and we are going to blast sodium. Now, let's write the electron configuration for sodium first. All right, so if we blast sodium with a laser, the electrons that are most likely to be torn away, to be lost, are going to be these valence electrons. Why? Because they are further from the nucleus, okay, and have the least attractive force between the nucleus and the valence electron. So we're going to lose that 3s1 electron, okay, because it is the least, okay, least tightly held. Furthest from the nucleus. Okay. So blast away with the laser again. Okay. Which electrons are least likely to be torn? Well, in sodium, it's going to be these 1s2 electrons. Those feel the full force of the nucleus. They're closest to the nucleus. Okay. So most attraction to nucleus. Okay. Most attractive force, we should say. Okay, closest to the nucleus. Okay, so this energy required to remove an electron from a gaseous atom or ion is called the ionization energy. Okay, so we start off by removing the easiest ones first, and then we go on to the next easiest, and then the next easiest, and the next easiest. And so this first ionization energy of sodium is Na gaseous atom goes to Na plus gaseous ion plus an electron. Okay, so that's the process for the first ionization energy. The second ionization energy is going to take that ion, okay, the gaseous ion, and remove another electron from the gaseous ion and make the sodium into sodium 2 plus, and then an electron that flies away. Okay, so that's our ionization energy. All right, so we blast away with the laser. Okay, what happens to the charge? Well, the charge goes up. More positive. Right, we remove our negative electrons, we become more positive. Just like if you lose your negative thoughts, you become more positive. What happens to the size of the atom or ion as electrons are removed? Well, as we saw before, the size goes down. Okay, and this size, okay, the size of an atom is called the atomic radius. The size of an ion is called the ionic radius. And the reason why size is in parentheses is because there are many different ways that size is defined depending on the context of the bonding and the material. So that's why I put size in parentheses. Okay, so that finishes up 1.5, topic 1.5 on electron configuration, and I threw in some periodic trend stuff as well. Now we're going to move on to topic 1.6, which is on photoelectron spectroscopy, abbreviated PES. PES is one way to show evidence that the shell model, the orbital model, the Bohr model is a valid model for the atom. Here we have some PES instrumentation right here. Okay, And going to this slide. So first of all, just like the mass spectrometer, you do not need to be able to explain how a PES instrument works, okay? What you do need to be able to do is interpret the spectrum that you get from the instrument. So basically in PES, what happens is you send very energetic X-rays, very, very high energy. I worked on a machine that had X-rays that went up to 1487 electron volts. If this X-ray hit you, you'd just blast right through your arm, through your skin. So stay away from X-rays. So you blast the atoms with X-rays, and the X-rays start blasting electrons out of the atom from anywhere in the atom. Not necessarily just the easiest ones, but all of the atoms. If they get blasted with enough energy, the electrons will just, will be blasted out. Okay, and as you blast those electrons in the atom with energy, they start leaving the sample, and the amount of kinetic energy that they leave with, okay, depends on, of course, the X-ray energy. This is fixed. Depends on the binding energy of the electron, how tightly the electron is bound to the nucleus. Okay, and then these go through this charged hemisphere, which bends the slower electrons because they're slower, and the faster electrons less. And so these will get separated out by kinetic energy, which will allow you to distinguish the binding energy of these various electrons. So then you start counting up, you'll see, oh, they'll start piling up here and make these peaks. Okay. So here's just another schematic. The X-ray comes in and it knocks out, okay, in this case, a 1s electron. Okay, so, and so this is based on the photoelectric effect. We will talk more about this later. This is what Einstein received a Nobel Prize for in the early 1900s. And so using, this is based on the photoelectric effect, which basically is this equation right here. And right below is an actual PES spectrum. This comes from a type of PES instrument called XPS, X-ray photoelectron spectroscopy. So here they're blasting barium oxide. So you can see barium, different peaks from different electrons in different subshells of barium. And then you can also see the oxygen peaks. And then, oh, there might be a little bit of carbon there. It's hard to get rid of carbon from PES samples. Okay, so here's a very stylized, nice, ideal, pretty PES data. You're never going to see anything like this in the actual laboratory. Okay, but on the AP exam, guess what? They're going to give you nice, pretty pictures like this. So first of all, two things to notice. Okay, this axis, the y-axis, is the relative number of electrons. So we can kind of see the relative numbers. So for example, this 2p6 has 6 electrons. The 2s2 has 2 electrons. The 2p6 is 3 times higher than the 2s2, okay, because it has 3 times more electrons. The energy down here is called the binding energy, the energy required to remove the electrons, how tightly they're bound to the nucleus. And the weird thing is that this is higher here, and this is lower. Okay, so it goes from low to high this way. The left side represents higher binding energy. The right side is lower binding energy. The reason why they do the spectrum like this is so that it models, okay, let's say this right here is the nucleus. Okay, and then this would mean this 1s2 is right next to the nucleus, then 2s2, 2p6, 3s2, 3p1, and so forth. So that's the reason why they've made the axis go, the x-axis, the energy go from high to low. All right, each peak is going to represent a different sublevel. Okay, the leftmost peak, okay, if they tell you it's a full spectrum, is going to be 1s2, and then it will continue on based on the electron configuration of the element. Okay, so let's look at an example. Here we have two spectra. One is black, one is red, and they represent two different elements. So which element is represented by the black peaks? Well, again, if this is a full spectrum, which we're going to assume it is, this first black peak is 1s2, then it's 2s2 here, and then this next black peak is twice as high, right? We can see that it's twice as high. This is 2 electrons here, 2 electrons, so this is 2p4. Okay, that would be 4 plus 2 plus 2. That means that this is oxygen. 8 electrons. Okay, so now let's look at the red peaks. So these red peaks, again, we have 1s2, 2s2. Okay, this one's the same height, so this must be 2p2, has the same number of electrons in the 2p as in the 2s. So now we have 2 plus 2 plus 2, that's 6 electrons. So the red, okay, must be carbon. Okay, so now explain to your mate, why the black peaks of oxygen are on the left, okay, of the carbon peaks. Well, what's different about carbon and oxygen? Well, these 1s electrons, let's just look at the 1s electrons for carbon. Well, this is oxygen. Okay. Oxygen. Okay, we'll just look at the 1s peaks, and this is carbon. The nucleus here, okay, is +8. Here for carbon, it's +6. Coulomb's law says that higher the charges, the more attractive force. Okay? More protons means higher positive charge in the nucleus, more attractive force on the electrons. More attractive force means that the binding energy is higher. And remember that the x-axis goes from high to low. So going to the left means it requires more energy to remove these 1s electrons from oxygen because there is a higher nuclear charge because of more protons in the nucleus. Okay, and again here, this is recapping what I just explained. All right, so then you got to do these PS questions, and we had a quiz, and that ends the day's lesson. I won't do the lab protocols in this class video. Maybe I'll do that separately in some other video, but this ends the topics 1.5 and 1.6.